Tonight, we're going to explore something that sounds straightforward, but is actually one of the most haunting mysteries in all of science: cosmic isolation. Why Earth is the loneliest planet. You've probably heard about the search for extraterrestrial life countless times. Scientists tell us there are hundreds of billions of stars in our galaxy alone, with potentially trillions of planets. The math seems to suggest we should have company. But here's what most people don't realize. When you actually look at the evidence, when you examine the profound silence that surrounds us, you discover something deeply unsettling. Despite all those worlds, despite all that potential for life, we appear to be completely alone. Not just rare, alone. This isn't about whether life exists elsewhere. It's about why, in a universe that should be teeming with intelligence, we're still listening to nothing but cosmic static. By the end of tonight, you're going to understand why this silence might be the most important mystery our species has ever faced, and what it reveals about the true nature of existence itself. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small gesture for you, but it makes a huge difference for me. Now, let's begin. Picture this moment, right now, wherever you are. The sun has set, darkness has settled around you, and you're part of something extraordinary that most of us take completely for granted. You're sitting on a small rocky planet that spins through space, carrying with it something almost impossibly rare. Billions of minds capable of wondering about their place in the cosmos. Every light you see glowing in windows around you, every screen illuminating a face, every street lamp cutting through the darkness represents consciousness at work, thoughts forming, questions being asked, dreams taking shape. You are part of Earth's great experiment in awareness, a living island of curiosity floating in an ocean of silence so vast and complete that it defies our ability to truly comprehend it. When you look up at the night sky from your backyard or through your bedroom window, you see what appears to be a beautiful tapestry of distant lights scattered across the darkness. Stars by the thousands, galaxies containing hundreds of billions more stars, each potentially surrounded by worlds of their own. The scale suggests abundance beyond imagination. Modern astronomy tells us there could be more planets in our galaxy alone than there are grains of sand on all of Earth's beaches. With numbers like that, with such staggering cosmic real estate, the universe should be a bustling neighborhood filled with the radio chatter of countless civilizations, the lights of vast cities, the signatures of intelligence reaching across space to touch other intelligence. Yet here you sit in the darkness, and the cosmos remains stubbornly, mysteriously quiet. This isn't simply an absence of sound, because sound cannot travel through the vacuum of space anyway. This is something far more profound and unsettling. It's the absence of any clear sign that we share this universe with minds like ours. No intentional signals received by our radio telescopes. No obvious megastructures blocking distant starlight in patterns that could only be artificial. No spacecraft appearing in our skies with intentions we could recognize as intelligent. The silence isn't just acoustic, it's informational. After more than 60 years of serious searching, after scanning thousands of star systems and listening across vast ranges of the electromagnetic spectrum, we have detected exactly 0 confirmed messages from other technological civilizations. This silence has a quality that goes beyond the merely physical. When scientists speak of the loneliness of Earth, they're describing something that operates on multiple levels simultaneously, each one compounding the others in ways that can leave even the most optimistic researchers feeling a profound sense of cosmic solitude. The first kind of loneliness is spatial, and it's the easiest to understand even though the distances involved break most people's ability to visualize them meaningfully. The nearest star to our Sun is Proxima Centauri, sitting about 25 trillion miles away. If you could somehow travel at the speed of light itself, racing across space faster than anything in the universe can move, it would still take you over 4 years to reach that closest stellar neighbour. At the speed of our fastest spacecraft, the journey would require tens of thousands of years. But distance in space is just the beginning of our isolation. There's also temporal loneliness, the possibility that we might be separated from other civilizations, not just by gulfs of space, but by gulfs of time. Consider that Earth has existed for about 4.5 billion years, while human civilization represents only the tiniest fraction of that span. If another technological species had emerged on a planet circling Proxima Centauri just 50,000 years ago, their entire rise and fall might have occurred while our ancestors were still learning to control fire. They could have built cities, developed science, reached for the stars, and vanished back into cosmic dust long before we developed the first tools capable of detecting their existence. Alternatively, intelligence might be emerging on distant worlds right now, taking its first tentative steps toward technology and space travel. But we won't be around to witness their radio signals for hundreds of thousands of years. Then there's informational loneliness, perhaps the most subtle but equally isolating form of separation. Even if two civilizations exist at the same time and manage to detect each other across interstellar distances, the simple exchange of information becomes an exercise in geological patience. A radio message sent from Earth to Proxima Centauri takes over 4 years to arrive. If anyone there receives it and sends a response, we wait another 4 years for the reply to reach us. A simple conversation, the kind you might have with a friend over coffee, becomes a decades-long exchange between generations. The natural rhythm of question and answer, the back and forth that defines communication between minds, stretches across time scales longer than most human careers. This is why Earth feels like an island of consciousness in a dark sea, even in a universe that might be rich with life. You're part of a world where millions of species have learned to communicate with each other in countless sophisticated ways. Whales sing across ocean basins. Trees share resources and information through underground fungal networks. Birds navigate by magnetic fields and stellar patterns. Humans have developed languages and mathematics and art, creating elaborate systems for sharing the contents of our minds with other minds. Yet for all this internal richness, for all the complex conversations happening on our planet at every moment, we remain cut off from any larger community of consciousness by distances so vast and communication delays so extreme that they might as well be infinite. The loneliness of Earth isn't necessarily permanent, and it doesn't mean we're actually alone in the universe. What it means is that if other thinking beings exist out there among the stars, they face the same fundamental challenges we do. They sit on their own islands of awareness, looking up at their own night skies, wondering if anyone else is wondering about them. The universe might be filled with such islands, each one rich with life and thought and dreams, yet each one isolated by the simple, implacable physics of distance and time. When astronomers talk about our nearest stellar neighbours, they use a unit of measurement that sounds deceptively familiar, and yet represents distances so extreme that your mind will struggle to hold on to their true meaning. They speak of light years, and you've heard this term thousands of times, probably since you were a child first learning about space. But pause for a moment and consider what this measurement actually represents, because understanding a light year is the first step toward grasping why the cosmos feels so profoundly empty around us. A light year isn't a measure of time, despite how it sounds. It's a measure of distance, and specifically, it's the distance that light travels in exactly 1 Earth year. Now, light moves faster than anything else in the universe. Nothing can exceed its speed, and most things can't even come close. Light races through empty space at approximately 186,000 miles per second. To put that in perspective, light can circle the entire Earth at its equator more than 7 times in just 1 second. It can travel from New York to Los Angeles in about 16 milliseconds. The light from your bedside lamp reaches your eyes so quickly that there's no meaningful delay between switching it on and seeing its glow. Yet even at this incredible speed, light still takes time to cross the vast emptiness between stars. When light leaves the surface of our sun, it takes about 8 minutes to reach Earth. That means when you look up at the sun, you're seeing it as it was 8 minutes ago, not as it is right now. The light that left the sun's surface when you started reading this paragraph is only just now arriving at Earth. This 8-minute journey covers about 93 million miles, which astronomers call 1 astronomical unit, a distance that already challenges our everyday sense of scale. But here's where the numbers become truly mind-bending. If light travels 93 million miles in 8 minutes, how far does it travel in an entire year? The answer is approximately 5.8 trillion miles. That's 5,800 billion miles. That's a 6 followed by 12 zeros. That single light year represents a distance so vast that if you could somehow build a highway stretching that far and drive along it at 70 miles per hour without ever stopping to rest, eat, or sleep, your journey would take more than 9 million years to complete. Now, armed with this understanding of just how immense a single light year is, you can begin to appreciate the true isolation of our solar system. Our nearest stellar neighbour isn't another solar system just beyond Pluto's orbit, some manageable distance that we might conceivably visit with advanced rockets. Our nearest neighbour is Proxima Centauri, a small red dwarf star that sits approximately 4¼ light years away from us. That means the light you see from Proxima Centauri tonight left that star more than 4 years ago, when the world was a measurably different place. The light reaching your eyes right now began its journey before the most recent presidential election, before countless personal milestones in your own life, carrying with it information about how that distant star appeared in what is, from our perspective, the relatively distant past. To truly grasp what 4¼ light years means in terms of physical distance, imagine that our entire solar system, from the Sun out to the orbit of Neptune, could somehow be shrunk down to the size of a small coin sitting on your table. On that scale, Proxima Centauri wouldn't be sitting across the room or even across town. It would be located more than 400 miles away. The nearest star to our Sun is farther from us, proportionally, than Boston is from Philadelphia, or than London is from Edinburgh. Except instead of hundreds of miles, we're talking about 25 trillion miles of mostly empty space stretching between our two stellar neighbourhoods. The Alpha Centauri system, which includes Proxima Centauri, along with 2 other stars called Alpha Centauri A and Alpha Centauri B, represents our closest stellar neighbours, the cosmic equivalent of the house next door. Yet reaching even this closest neighbour with our current technology would require a journey lasting tens of thousands of years. The Voyager 1 spacecraft, which has been travelling away from our solar system for more than 4 decades and is now racing through interstellar space at roughly 38,000 miles per hour, would still need more than 70,000 years to reach Proxima Centauri if it were actually headed in that direction. This is the fundamental challenge that defines our cosmic loneliness. Even our immediate stellar neighbourhood, the small collection of stars that represent our closest possible neighbours in the galaxy, exists at distances that make casual visitation impossible with any technology we can currently imagine. We're not talking about difficult journeys that might require generations of travellers or revolutionary new propulsion systems. We're talking about distances so extreme that they dwarf human civilization itself. The entire recorded history of our species, from the first written languages to the present day, spans less time than it would take our fastest current spacecraft to reach the nearest star. Yet this nearest neighbour, sitting 4¼ light years away across an ocean of vacuum, represents just the first step in a cosmic distance ladder that stretches beyond comprehension. The next nearest stars are twice as far. Others are 10 times as far, or 100 times as far. Our galaxy contains hundreds of billions of stars, yet most of them are separated from us by distances that make even Proxima Centauri seem relatively close. The majority of stars visible to your naked eye on a clear night are dozens or hundreds of light years away. Some of the brightest stars in familiar constellations are thousands of light years distant, so far that their light began its journey toward Earth before human civilization began. This is why astronomers speak of interstellar space with such reverence, and why the search for extraterrestrial intelligence requires such profound patience. We live in a universe where even the closest possible neighbours exist at distances that transform simple communication into multi-generational projects and make physical contact seem almost impossibly remote. Humanity has managed to build and launch the fastest messengers we've ever created, mechanical emissaries carrying our voices and our dreams beyond the familiar boundaries of our solar system. These spacecraft represent the pinnacle of our current ability to reach across interstellar distances, and their journeys offer us the most concrete way to understand just how vast and challenging the cosmos really is. When you consider what these remarkable machines have accomplished and how slowly they move by cosmic standards, you begin to grasp why the universe feels so quiet around us, and why even our most ambitious attempts to bridge the gaps between stars require a kind of patience that spans multiple human lifetimes. The most famous of these cosmic messengers is Voyager 1, a spacecraft about the size of a small car that launched from Earth in 1977, carrying scientific instruments, cameras, and a golden record filled with sounds and images from our planet. For more than 4 decades, Voyager 1 has been racing away from the Sun at approximately 38,000 miles per hour, a speed that represents the fastest any human-made object has ever travelled on a sustained basis. To put this velocity in perspective, Voyager 1 could fly from New York to Los Angeles in about 4 minutes. It could circle the Earth's equator in just over an hour. By the standards of human transportation, this spacecraft moves at almost incomprehensible speed. Yet when measured against the scale of interstellar space, Voyager 1 crawls with geological slowness. Currently, this fastest of human messengers is travelling at roughly 3.6 astronomical units per year, gradually working its way through the outer regions of our solar system's influence and into the space between stars. An astronomical unit, remember, is the distance from Earth to the Sun, approximately 93 million miles. So Voyager 1 covers about 335 million miles every year, a distance that would encompass more than 14,000 trips around Earth's circumference. This sounds impressively fast until you calculate what it means for reaching other stars. At its current pace, Voyager 1 would require approximately 17,000 years to travel just 1 light year. Since our nearest stellar neighbour, Proxima Centauri, sits more than 4 light years away, Voyager 1 would need roughly 73,000 years to complete the journey, assuming it were actually headed in that direction. To put this time span in historical context, 73,000 years ago, modern humans were just beginning to migrate out of Africa. The entire span of recorded human history, from the first written languages to the present day, covers less than 6,000 years. Voyager 1 would need more than 12 times longer than all of human civilization to reach the nearest star. Even if we could somehow build spacecraft 10 times faster than Voyager 1, the journey to Proxima Centauri would still require more than 7,000 years, longer than the entire span of written history. If we could achieve speeds 100 times faster than our current record holder, we'd still be looking at a journey of more than 7 centuries, longer than the time that has passed since the Renaissance. These numbers aren't meant to discourage, but rather to illustrate the fundamental challenge posed by interstellar distances. The universe is built on a scale that dwarfs not just individual human lifetimes, but entire civilizations. Voyager 1 carries with it a golden record, a metal disc containing sounds and images chosen to represent the diversity of life and culture on Earth. This record includes everything from the sound of wind and rain to musical selections from different cultures, mathematical definitions, and spoken greetings in dozens of human languages. The idea behind this cosmic message in a bottle was that if any other intelligence ever encountered Voyager 1 in the depths of space, they would find an introduction to our world and our species. It's a beautiful and optimistic gesture, a way of reaching across the cosmic dark to say, we were here, we existed, we thought and felt and created. But the golden record also serves as a sobering reminder of the timescales involved in interstellar communication. Even if Voyager 1 were intercepted by another intelligence tomorrow, which is statistically almost impossible given the vastness of space, any response would take years to reach us, and that assumes the interceptors possess technology capable of sending signals back toward our solar system. More realistically, if Voyager 1 is ever found by another intelligence, it will likely happen tens of thousands of years from now, when Earth and human civilization may be unrecognizably different from what we know today. The two Voyager spacecraft, along with Pioneer 10 and Pioneer 11, represent humanity's first serious attempts to send physical messages beyond our solar system. They are our bottles cast into the cosmic ocean, carrying with them proof that intelligence arose on at least one small rocky planet orbiting a yellow star in the outer regions of the Milky Way galaxy. These spacecraft will likely outlast human civilization itself, continuing their silent journeys through interstellar space long after the last human voice has fallen quiet on Earth. This perspective transforms how we think about communication across interstellar distances. When scientists search for signals from other civilizations, they're not looking for conversations in any sense we would recognize. They're looking for evidence that someone else once threw their own bottles into the cosmic ocean, perhaps thousands or millions of years ago. The radio telescopes scanning the sky are essentially beachcombers, searching the cosmic shoreline for messages that may have been traveling toward us since before our species existed. The profound slowness of our fastest messengers reveals why the cosmos feels so empty around us. Even if other civilizations exist at nearby stars, even if they've been trying to communicate or explore for thousands of years, the simple physics of distance and speed means that their messages and their messengers are still crossing the vast gulfs between stars, traveling through decades or centuries of empty space before they might reach us. When you imagine traveling to other stars, your mind probably conjures images of sleek spacecraft accelerating smoothly through space, perhaps powered by exotic engines that make interstellar journeys seem as routine as flights between continents. Science fiction has given us countless visions of starships that slip easily between worlds, making the galaxy feel like a navigable ocean where distance is merely an inconvenience to be overcome with better technology. But the reality of space travel reveals something far more fundamental and unforgiving about the structure of our universe. Space doesn't behave like an ocean or a highway. It behaves like an enormous moat, and the physics that govern motion through this moat create barriers so formidable that they transform the cosmos into a collection of isolated islands rather than a connected empire. The first and most fundamental challenge comes from a deceptively simple principle that Isaac Newton identified more than 3 centuries ago. An object in motion tends to stay in motion, and an object at rest tends to stay at rest, unless acted upon by an outside force. This principle, known as inertia, governs everything that moves through space, from dust particles to massive spacecraft. When you're sitting in your chair right now, you feel stationary, but you're actually racing through space at enormous speed as Earth rotates and orbits the Sun. You don't feel this motion because you and everything around you are moving together, maintaining the same velocity through space. To travel between stars, a spacecraft must change its velocity dramatically, accelerating from the speed it shares with Earth to whatever speed is necessary for interstellar travel. This change in velocity requires energy, and the faster you want to go, the more energy you need. This relationship isn't linear, where going twice as fast requires twice as much energy. Instead, the energy requirements follow what physicists call a square law. Going twice as fast requires 4 times as much energy. Going 3 times as fast requires 9 times as much energy. Going 10 times as fast requires 100 times as much energy. This mathematical relationship means that relatively modest increases in speed demand enormous increases in the energy needed to achieve them. But here's where the challenge becomes truly daunting. Unlike a car, which can carry a small amount of fuel relative to its own weight and refuel regularly along the journey, a spacecraft traveling between stars must carry all of its energy with it from the beginning of the trip. There are no gas stations in interstellar space, no way to stop and refuel halfway through a journey that might last thousands of years. Every bit of energy needed for acceleration, course corrections, and deceleration at the destination must be loaded into the spacecraft before it leaves Earth. This creates what rocket engineers call the tyranny of the rocket equation, a mathematical relationship that reveals why space travel becomes exponentially more difficult as you try to go faster or farther. The problem is that fuel has weight, and that weight must also be accelerated along with the spacecraft itself. If you want to go faster, you need more fuel, but more fuel means more weight, which means you need even more fuel to accelerate that additional weight, which adds more weight that requires still more fuel. This spiral continues until the fuel requirements become absurdly large. To understand how quickly these requirements grow, consider a hypothetical journey to Proxima Centauri. If you wanted to build a spacecraft that could reach 10% of the speed of light, fast enough to complete the journey in about 40 years, the fuel requirements using current chemical rocket technology would be truly staggering. Even if your actual spacecraft, the part carrying people and equipment, weighed only as much as a small car, the fuel needed to accelerate it to 10% of light speed would have a mass comparable to a mountain. The entire mass of fuel would dwarf the payload by factors of millions or billions. This is why more advanced propulsion concepts, like nuclear rockets or fusion drives, become necessary for any serious discussion of interstellar travel. These technologies can extract much more energy from each unit of fuel, reducing the total fuel requirements somewhat. But even with these advanced systems, the energy demands for high-speed interstellar travel remain enormous. The fundamental physics doesn't change. The rocket equation still applies. You still need to carry all your energy with you, and you still face exponentially increasing costs as you try to achieve higher speeds. Some proposed solutions attempt to work around these constraints by avoiding the need to carry conventional fuel. Solar sails use pressure from starlight to provide gentle acceleration over long periods. Concepts like laser-propelled light sails could potentially accelerate small payloads to significant fractions of light speed by beaming energy from powerful Earth-based lasers. But these approaches come with their own severe limitations. Solar sails work only near stars, where sunlight is strong enough to provide meaningful thrust. Laser propulsion works only for extremely lightweight payloads over relatively short distances before the laser beam spreads too widely to be effective. The profound difficulty of interstellar travel isn't a temporary limitation that we'll overcome with better engineering. It's a fundamental feature of how the universe works. Space is vast, not just in terms of distance, but in terms of the energy required to cross those distances at meaningful speeds. The emptiness between stars isn't merely empty space waiting to be filled with our ambitions. It's a barrier constructed from the basic laws of physics, a moat so wide and deep that it naturally separates stellar systems from one another. This physical isolation has profound implications for how life and intelligence might be distributed throughout the galaxy. Rather than forming connected networks or expanding empires, civilizations are more likely to exist as isolated islands, each developing independently on their own worlds around their own stars. The vast energy costs of interstellar travel mean that even advanced civilizations would find it difficult to establish permanent connections across multiple star systems. Space behaves like a protective moat around each world, preserving the independence and isolation of whatever life might arise there. When you step outside on a clear night, far from city lights, and look up at the star-filled sky arching overhead, you're seeing just the tiniest fraction of our cosmic neighborhood. The few thousand stars visible to your naked eye represent less than 1% of the stellar population that surrounds you. You're looking at the local suburbs of a structure so vast and so densely packed with suns that it challenges every intuitive sense of scale you've developed throughout your life. This structure is our home galaxy, the Milky Way, and understanding its true dimensions reveals why the cosmos can be simultaneously crowded with potential worlds and yet still profoundly isolated in ways that make meaningful contact between civilizations extraordinarily unlikely. The Milky Way stretches approximately 100,000 light-years from edge to edge, a disk of stars, gas, and dust rotating slowly through space like an enormous cosmic pinwheel. To grasp what 100,000 light-years means, remember that a single light-year represents nearly 6 trillion miles, a distance so vast that our fastest spacecraft would need tens of thousands of years to traverse it. Now multiply that already incomprehensible distance by 100,000, and you begin to approach the true scale of our galactic home. If you could somehow travel at the speed of light itself, racing across space faster than anything in the universe can move, it would still take you 100,000 years to cross from one side of the Milky Way to the other. This galactic disk contains what astronomers estimate to be somewhere between 100 billion and 400 billion individual stars, each one a sun potentially capable of warming worlds of its own. The uncertainty in this number isn't a sign of sloppy science, but rather a testament to the sheer scale involved. Counting stars across such vast distances presents technical challenges that leave room for uncertainty even in our most sophisticated estimates. But even taking the lower estimate of 100 billion stars, you're looking at a number so large that if you started counting stars at the rate of 1 per second, working without rest 24 hours a day, you would need more than 3,000 years to count them all. These numbers suggest abundance beyond imagination. 100 billion stars means 100 billion potential solar systems. If even a tiny fraction of those stars host planets, and if even a tiny fraction of those planets develop life, and if even a tiny fraction of those living worlds eventually give rise to intelligence, the Milky Way could still contain millions or even billions of technological civilizations. The math seems to argue powerfully for a galaxy teeming with minds, a cosmic community of intelligence spread across countless worlds orbiting distant suns. Yet this same mathematical abundance reveals a profound paradox that lies at the heart of our cosmic loneliness. Even with 100 billion stars distributed across the galactic disk, the average distance between neighboring stars remains enormous by any human standard. If you could somehow distribute those 100 billion stars evenly across the volume of the Milky Way, each star would sit roughly 4 to 5 light-years away from its nearest neighbours. This is the same distance that separates us from Proxima Centauri, our actual nearest stellar neighbour, which means that our local situation isn't unusually isolated. we're experiencing the typical spacing that characterizes stellar neighborhoods throughout the galaxy. This reveals the crucial distinction between density and accessibility. The Milky Way is indeed dense with stars when you consider the total number packed into the galactic structure. 100 billion stars represents an almost unimaginable concentration of matter and energy, a collection of suns that collectively outweighs our entire solar system by factors of billions. But this density exists on a scale so vast that it doesn't translate into proximity in any meaningful sense. It's like being told that a desert contains millions of grains of sand, which sounds dense and crowded, until you realize that each grain of sand is separated from its neighbors by miles of empty space. The galactic environment creates what you might think of as a cruel mathematical joke. There are so many stars that some of them almost certainly host worlds with life, perhaps even intelligent life. The numbers are so large that it becomes statistically almost impossible for Earth to be unique in the galaxy. Yet these potentially inhabited worlds are distributed across distances so vast that they might as well exist in separate universes as far as communication and travel are concerned. Even if our nearest stellar neighbours at Alpha Centauri possessed a thriving technological civilization, establishing meaningful contact would require the kind of long-term thinking and patience that spans many human generations. Scale this challenge across the entire galaxy, and the isolation becomes even more profound. A civilization located just 1,000 light-years away, still within our local galactic neighborhood, would be separated from us by distances that transform simple communication into projects lasting millennia. A radio signal sent to such a civilization today would not arrive until the year 3025. If they received it immediately and sent a response, we wouldn't hear back until the year 5025, more than 2 millennia into the future. Most of the stars in our galaxy are much farther away than 1,000 light-years. The galactic center, where stars are most densely packed, sits approximately 26,000 light-years from our solar system. Civilizations that might exist in those central regions face communication delays with us that span tens of thousands of years each way. By the time any message could travel from Earth to the galactic core and back, human civilization could rise and fall multiple times over. This is the paradox of our galactic home. The Milky Way contains enough stars to make the existence of other intelligent life statistically almost certain, yet it spreads those stars across distances so enormous that the galaxy functions less like a community and more like a collection of isolated islands, each one potentially rich with life and thought, but each one fundamentally alone in the cosmic dark. In the span of just a few decades, astronomers have achieved something that would have seemed like pure fantasy to previous generations of scientists. They have conducted a census of worlds beyond our solar system, methodically cataloguing planets orbiting distant stars with a precision and scope that transforms our understanding of how common planetary systems actually are throughout the galaxy. This astronomical revolution began in earnest in the 1990s and has accelerated dramatically with space-based observatories designed specifically for planet hunting. As of today, NASA's official tally has reached over 6,000 confirmed exoplanets, with thousands more candidates awaiting verification through additional observations and analysis. This number represents one of the most remarkable scientific achievements in human history. For thousands of years, people looked up at the stars and wondered whether other worlds existed out there in the cosmic dark. Philosophers debated the question. Scientists speculated about it. Science fiction writers built entire genres around the possibility. But until very recently, the existence of planets beyond our solar system remained pure speculation, an intriguing idea that could neither be confirmed nor denied with the observational tools available to astronomers. The revolution began with the detection of the first confirmed exoplanet orbiting a Sun-like star in 1995. This world, designated 51 Pegasi b, shattered many assumptions about how planetary systems form and evolve. It was a gas giant planet orbiting incredibly close to its star, completing an orbit in just over 4 days and experiencing surface temperatures hot enough to melt metal. This was nothing like the orderly arrangement of planets in our own solar system, where gas giants like Jupiter and Saturn orbit at comfortable distances from the Sun, while smaller rocky planets occupy the inner regions. The discovery of 51 Pegasi b opened the floodgates. Ground-based telescopes began, detecting more and more exoplanets using increasingly sophisticated techniques. Some discoveries came from detecting the tiny gravitational wobble that an orbiting planet induces in its host star. Others came from observing the minute dimming that occurs when a planet passes in front of its star as seen from Earth, temporarily blocking a small fraction of the starlight. Each detection required months or years of careful observation, painstaking data analysis, and rigorous verification to distinguish genuine planetary signals from instrumental noise or other astrophysical phenomena. Then came the space telescopes designed specifically for planet hunting, and the pace of discovery accelerated exponentially. The Kepler Space Telescope, launched in 2009, monitored more than 150,000 stars simultaneously, watching for the telltale dimming that indicates a planetary transit. Over its operational lifetime, Kepler discovered thousands of confirmed planets and identified thousands more candidates. The Transiting Exoplanet Survey satellite, known as TESS, continues this work today, scanning the entire sky for worlds orbiting the nearest and brightest stars. This census of worlds has revealed a universe far stranger and more diverse than anyone anticipated. Astronomers have found planets made of diamond, worlds where it rains glass sideways in supersonic winds, planets orbiting so close to their stars that their surfaces are molten lava, and ice giants drifting in the cold outer regions of distant solar systems. They've discovered planets orbiting binary star systems, worlds that experience sunsets from two different suns. They found planets smaller than Mercury and planets more massive than Jupiter, worlds with densities lower than cork and others denser than lead. Most significantly, they've identified thousands of planets orbiting within what astronomers call the habitable zone, the range of distances from a star where liquid water could potentially exist on a planet's surface. These worlds, sometimes called Goldilocks planets because they're neither too hot nor too cold but just right for liquid water, represent the most promising candidates for harbouring life as we know it. The nearest confirmed habitable zone planet, Proxima Centauri b, sits just over 4 light-years away, orbiting our closest stellar neighbour. Yet here's the profound irony embedded in this remarkable census of worlds. The more planets we discover, the more isolated Earth begins to feel. Each new detection confirms that planetary systems are common throughout the galaxy, that worlds of all descriptions orbit billions of stars across the Milky Way. This abundance should make the universe feel crowded and connected, a cosmic community of worlds linked by their shared existence as oases of solid matter in the vast ocean of space. Instead, the opposite has happened. Every new exoplanet discovery serves as a reminder of how unreachable these worlds are with our current technology and how unlikely it is that we'll ever know whether they harbour life. Finding a planet orbiting a star 50 light-years away tells us that the planet exists, but it doesn't bring us any closer to visiting it or communicating with anyone who might live there. The detection itself required years of careful observation just to confirm that the world exists. Actually reaching it would require journeys lasting tens of thousands of years. The census of worlds has created a new kind of cosmic loneliness, more subtle but perhaps more profound than the loneliness we felt when we didn't know whether other worlds existed at all. Now we know they're out there by the thousands, scattered across distances that make them forever inaccessible. We can detect them, study their basic properties, and speculate about what conditions might exist on their surfaces. But discovery is not visitation. Detection is not communication. Knowledge of their existence is not connection. We're learning to find planets with remarkable precision and efficiency. The question that emerges from this success is whether we'll ever be able to determine if any of these distant worlds harbour life, and whether such knowledge would bridge the cosmic isolation or simply make it more poignant by confirming that we share the galaxy with other forms of consciousness that we can never hope to meet. Beyond the vast gulfs of space that separate star from star lies another form of isolation that may be even more profound and insurmountable. This is temporal isolation, the separation that exists not across distances measured in light years, but across spans of time that can render civilizations invisible to each other even when they arise on neighboring worlds. While we often focus on the spatial challenges of interstellar communication and travel, imagining the day when better rockets or more powerful radio telescopes might bridge the gaps between stars, we rarely consider how time itself creates barriers that no amount of technological advancement can overcome. Consider two hypothetical worlds orbiting stars just 4 light-years apart, near neighbours by galactic standards. On the first world, an intelligent species evolves, develops agriculture, builds cities, discovers science, and eventually reaches into space with radio telescopes and spacecraft. This civilization flourishes for 10,000 years, a span that encompasses the entirety of human recorded history from the first written languages to the present day. They spend centuries listening for signals from other worlds, broadcasting their own messages into the cosmic dark, and developing increasingly sophisticated methods for detecting signs of intelligence among the stars. But on the neighbouring world, intelligence evolves at a different pace. Perhaps the planet experiences a slightly different evolutionary history, with ice ages that last longer or shorter, with continents arranged in patterns that encourage or discourage the spread of early civilizations, with resources distributed in ways that accelerate or delay technological development. This civilization begins its rise to intelligence just as the first civilization enters its final decline. By the time the Second World develops radio astronomy and begins its own search for cosmic companions, the first civilization has already vanished, leaving behind only the faintest archaeological traces on a world that has moved on to other forms of life. These two civilizations, separated by just 4 light-years of space, a distance that seems almost intimate by galactic standards, never overlap in time sufficiently to detect each other. If the first civilization had known to look, they would have seen only a planet with primitive life, perhaps simple multicellular organisms or early plants, showing no signs of the intelligence that would eventually arise there. If the second civilization aims their telescopes toward the first world, they see only the afterglow of a once great culture, a planet returning to its pre-technological state with no obvious signatures of the remarkable minds that once contemplated the stars from its surface. This temporal mismatch represents one of the most sobering possibilities embedded in the search for extraterrestrial intelligence. The galaxy may be rich with civilizations, but they exist like waves on a cosmic ocean, rising and falling on timescales that rarely allow them to crest simultaneously. Each world that gives rise to intelligence follows its own trajectory through time, influenced by countless local factors that determine when intelligence emerges, how long it persists, and what form it takes during its tenure. The lifetime of a technological civilization represents one of the greatest unknowns in all of astrobiology. How long, on average, does a species remain technologically active once it develops the ability to communicate across interstellar distances? This question has no clear answer because we have only one example to study: ourselves. Human civilization has possessed radio technology for barely more than a century, and our ability to detect signals from space spans only about 60 years. In cosmic terms, this represents the blink of an eye, a time span so brief that it provides almost no statistical basis for predicting how long technological civilizations typically last. Some scientists approach this question with optimism, suggesting that once a species develops advanced technology, it gains the tools necessary to solve most existential challenges and could potentially persist for millions or even billions of years. Others point to the various risks that accompany technological development, from environmental degradation to weapons of mass destruction to the simple tendency for complex systems to eventually fail, and suggest that the average lifetime of a technological civilization might be measured in thousands rather than millions of years. The truth likely lies somewhere between these extremes and probably varies dramatically from case to case. Some civilizations might discover sustainable ways of living that allow them to persist for geological timescales. Others might face insurmountable challenges that cut short their technological phase. Still others might choose to develop in directions that make them undetectable to our current search methods, pursuing technologies and lifestyles that leave no obvious signatures for distant observers to discover. This uncertainty about civilization lifetime compounds the challenges posed by spatial separation in ways that make the galaxy feel far lonelier than even the vast distances alone would suggest. If civilizations typically last only 10,000 years, and if they're separated by distances that make communication difficult even when they exist simultaneously, then the chances of any two civilizations overlapping in both space and time become vanishingly small. The galaxy could host thousands or even millions of civilizations across its history, with new ones constantly arising as others fade away, yet most of them would remain forever unknown to each other. The concept of temporal isolation also reframes how we think about our own place in cosmic history. We exist during one particular moment in the galaxy's long evolution, a moment characterized by certain stellar populations, certain chemical compositions in the interstellar medium, and certain patterns of star formation and planetary development. Other civilizations that arose billions of years ago experienced a galaxy with different characteristics, while civilizations that might arise billions of years from now will inhabit a cosmic environment we can barely imagine. This temporal dimension of cosmic loneliness suggests that the galaxy might be less like an empty house waiting for inhabitants and more like a vast boarding house where rooms are constantly occupied, but by tenants who arrive and depart on schedules that rarely overlap, leaving behind only faint traces for their successors to discover. In 1950, during a casual lunchtime conversation at Los Alamos National Laboratory, the physicist Enrico Fermi posed a question that has haunted astronomers and philosophers ever since. His colleagues were discussing the possibility of interstellar travel and the likelihood that other civilizations might exist somewhere among the stars when Fermi suddenly interrupted with four simple words that cut straight to the heart of cosmic loneliness. But where is everybody? This deceptively straightforward question, now known as the Fermi paradox, encapsulates one of the most profound puzzles facing modern science and challenges our most basic assumptions about life, intelligence, and our place in the universe. The logic behind Fermi's question appears almost unassailable when you consider the numbers involved. Our galaxy is approximately 13.6 billion years old, ancient enough to have hosted countless generations of stars and planetary systems. The Milky Way contains hundreds of billions of stars, many of them similar to our Sun, and we now know that planets are common throughout the galaxy. Even conservative estimates suggest that billions of worlds exist within the habitable zones of their stars, where liquid water could potentially exist on planetary surfaces. If life arose naturally on Earth through purely physical and chemical processes, as most scientists believe, then those same processes should have occurred on countless other worlds throughout galactic history. Moreover, once intelligence evolves on a world, it might be expected to expand outward, developing technology and eventually spreading to other planets and star systems. Even at relatively modest speeds, far slower than the speed of light, a single civilization could theoretically colonize the entire galaxy in just a few million years, a time span that represents less than 1% of the galaxy's total age. Given the immense age of the Milky Way, there has been ample time for intelligence to arise many times over, and for at least some of those civilizations to spread across vast regions of galactic space. Yet when we look around us, we see no clear evidence of such expansion. Our radio telescopes have been listening for artificial signals for more than 60 years without detecting any confirmed messages from other civilizations. Our spacecraft have visited every major body in the solar system without finding any obvious artifacts left behind by visiting aliens. Our most sophisticated instruments have searched for the kinds of large-scale engineering projects that advanced civilizations might undertake, such as structures built around entire stars to capture their energy, without finding convincing evidence that such projects exist anywhere in our galactic neighborhood. This absence of evidence has led to what Fermi identified as a fundamental contradiction between expectation and observation. The galaxy appears to offer countless opportunities for life and intelligence to develop, yet the cosmos around us seems remarkably quiet and empty of the signatures we might expect from a universe teeming with technological civilizations. This contradiction doesn't necessarily mean that we are alone in the universe, but it does suggest that our assumptions about the development and behavior of intelligent life may be profoundly incorrect. The Fermi paradox serves as a gentle reminder of how much we don't understand about the conditions necessary for life to evolve into intelligence and technology. It's important to recognize that this puzzle is not an argument against the existence of life elsewhere in the universe. The absence of evidence is not necessarily evidence of absence, particularly when we're searching for phenomena across distances and timescales that dwarf human experience. Instead, the Fermi paradox questions our assumptions about how common intelligence might be, how long technological civilizations typically last, and how readily they might expand across interstellar distances. When scientists attempt to resolve the Fermi paradox, their proposed solutions generally fall into four broad categories, each offering a different perspective on why the galaxy might appear so quiet despite its apparent potential for hosting life. The first possibility is that intelligent civilizations are genuinely absent, or at least extraordinarily rare. Perhaps the evolutionary path from simple organic molecules to technological intelligence is far more difficult and unlikely than we currently understand. Maybe Earth represents an unusual convergence of favorable conditions that rarely occur together elsewhere in the galaxy. The second possibility is that civilizations exist but remain quiet, either by choice or necessity. Perhaps intelligence naturally tends toward caution, with most civilizations choosing to listen rather than broadcast, remaining invisible to distant observers until they're confident that communication is safe. Alternatively, advanced civilizations might develop communication technologies that are invisible to our current detection methods, using quantum entanglement, neutrino beams, or other exotic phenomena that leave no trace in the electromagnetic spectrum we monitor. The third category suggests that civilizations are distant, separated from us by the vast scales of space and time we've already explored. Even if the galaxy hosts many intelligent species, they might be distributed so widely across the Milky Way that meaningful contact remains impossible with current technology. Additionally, they might be separated from us in time, arising and disappearing long before or after our own technological phase, creating temporal isolation that prevents any overlap in our respective periods of cosmic awareness. The fourth possibility is perhaps the most humbling. We may not be listening correctly. Our search for extraterrestrial intelligence has been limited by our assumptions about how other civilizations might choose to communicate, what kinds of signals they might send, and where we should look for evidence of their activities. We've been listening primarily for radio signals similar to those we ourselves broadcast, but alien intelligence might communicate in ways we haven't yet imagined or discovered. Each of these possibilities offers insights into the nature of intelligence, technology, and cosmic evolution, while acknowledging the profound uncertainties that surround our search for cosmic companions. The Fermi paradox doesn't demand a single answer, but rather invites us to question our assumptions and remain open to discoveries that might completely transform our understanding of life's place in the universe. In 1961, as the space age was just beginning and humanity was taking its first tentative steps toward understanding our place in the cosmos, an astronomer named Frank Drake was preparing for the first serious scientific meeting dedicated to the search for extraterrestrial intelligence. Faced with the challenge of organizing a discussion about a topic that had never been systematically studied, Drake realized he needed a way to structure the conversation around the fundamental question of how many communicating civilizations might exist in our galaxy at any given time. What he developed was not a formula designed to produce precise answers, but rather a framework for thinking clearly about profound uncertainty, a tool that would help scientists identify the key factors involved in the emergence and persistence of technological intelligence throughout the cosmos. The equation that bears Drake's name appears deceptively simple when written out, consisting of just 7 factors that, when multiplied together, theoretically yield an estimate of the number of communicating civilizations in the Milky Way. It begins with the rate at which new stars form in our galaxy each year, then multiplies this by the fraction of stars that develop planetary systems, then by the number of planets in each system that could potentially support life, then by the fraction of those planets where life actually develops, then by the fraction where life evolves into intelligence, then by the fraction where intelligence develops technology capable of interstellar communication, and finally by the length of time such civilizations remain active and detectable. At first glance, this mathematical approach might seem to promise definitive answers to questions that have puzzled humanity since we first looked up at the stars and wondered if we were alone. Simply plug in the appropriate values for each factor, perform the multiplication, and discover how many alien civilizations are out there waiting to be contacted. But Drake himself understood from the beginning that his equation's true value lay not in its ability to generate precise numbers, but in its power to organize our thinking about the problem and to highlight just how much we don't yet know about the conditions that give rise to intelligence in the universe. The brilliance of the Drake equation becomes apparent when you consider how little we actually know about most of its factors. The star formation rate in our galaxy represents one of the few components we can estimate with reasonable confidence, thanks to decades of astronomical observations that have mapped stellar populations and tracked the birth of new stars in stellar nurseries throughout the Milky Way. Similarly, the fraction of stars that host planetary systems has become much better understood in recent years, as space-based planet hunting missions have revealed that most stars appear to be accompanied by at least some planetary companions. But as you move through the remaining factors, the uncertainties multiply dramatically. The number of planets per system that could potentially support life depends heavily on how we define the habitable zone around different types of stars, and our understanding of this concept continues to evolve as we discover worlds that challenge our assumptions about where life might arise. The fraction of potentially habitable planets that actually develop life represents an even greater unknown, since we have only one confirmed example of a living world to study, making it impossible to determine whether the emergence of life represents an inevitable outcome given the right conditions or an extraordinarily unlikely accident that occurred only once in galactic history. The progression from simple life to intelligence introduces additional layers of uncertainty that compound the mystery further. On Earth, life existed for billions of years before evolving the kind of complex cognition we associate with technological intelligence. Whether this progression represents a natural tendency of evolution or a remarkable series of fortunate accidents remains one of the deepest unsolved questions in biology. Even if intelligence does emerge reliably on living worlds, the development of technology capable of interstellar communication might represent another unlikely step that occurred on Earth through a unique combination of circumstances. Perhaps most uncertain of all is the final factor: the length of time that technological civilizations remain active and detectable. As we've discussed, human civilization has possessed radio technology for barely more than a century, providing no statistical basis for estimating how long such capabilities typically persist. Do civilizations naturally evolve beyond the need for electromagnetic communication, developing technologies that render them invisible to our current search methods? Do they typically destroy themselves through war, environmental collapse, or other technological disasters? Or do they find ways to persist for millions or billions of years, creating a galaxy populated with ancient, stable civilizations that have simply chosen not to reveal themselves to newcomers like ourselves? When you multiply together a series of factors that range from reasonably well known to completely speculative, the resulting number becomes essentially meaningless as a quantitative prediction. Different scientists can plug their own estimates into the Drake equation and emerge with answers that range from much less than 1, suggesting we might be alone in the galaxy, to millions or billions, suggesting a cosmos teeming with intelligence. The equation doesn't resolve these disagreements. Instead, it reveals how much our conclusions depend on assumptions we cannot yet test. This is where the true genius of Drake's framework becomes apparent. Rather than providing false certainty about unknowable quantities, the equation serves as a powerful tool for disciplining our imagination and identifying the specific questions we need to answer if we hope to understand our cosmic context. It transforms vague speculation about alien life into a structured research program, highlighting the astronomical, biological, and sociological investigations that might eventually reduce our uncertainty about intelligence in the universe. The Drake equation teaches us that the search for extraterrestrial intelligence is not primarily about building more powerful telescopes or developing better detection algorithms, though these technical advances certainly matter. Instead, it's about gradually filling in our knowledge of the fundamental processes that govern the emergence and evolution of life and intelligence throughout the cosmos. Since the 1960s, a dedicated community of scientists has been engaged in one of the most patient and methodical searches in the history of human inquiry. Working with radio telescopes scattered across the globe, from the mountains of Puerto Rico to the high deserts of California, these researchers participate in an endeavor known as the Search for Extraterrestrial Intelligence, more commonly called SETI. Their work represents a fundamentally different approach to the question of cosmic loneliness than the ambitious schemes for interstellar travel we often imagine. Rather than building rockets capable of crossing the vast gulfs between stars, SETI researchers have chosen to listen, turning our most sensitive instruments toward the sky in the hope of detecting artificial signals that might reveal the presence of technological civilizations elsewhere in the galaxy. The basic premise behind SETI appears elegantly simple when stated plainly. If other technological civilizations exist among the stars, they might be using electromagnetic radiation to communicate, either among themselves or intentionally toward other worlds they hope might be listening. Radio waves and optical signals can travel at the speed of light across interstellar distances, making them far more practical for communication than any physical spacecraft. While it would take tens of thousands of years for even our fastest probes to reach the nearest stars, radio messages can cross those same distances in just a few years. A civilization with technology similar to our own could, in principle, send detectable signals across dozens or even hundreds of light years of space, using transmitters no more powerful than the largest radio telescopes we've already built on Earth. SETI researchers focus primarily on the radio portion of the electromagnetic spectrum because radio waves possess several characteristics that make them ideal for interstellar communication. Unlike visible light, radio waves can penetrate the dust clouds and gas that fill the space between stars, traveling across the galaxy without being significantly absorbed or scattered. Radio signals also require relatively little energy to generate and detect compared to other forms of electromagnetic radiation, making them economically feasible for civilizations that might want to maintain long-term communication projects spanning many years or centuries. The actual work of SETI involves using large radio telescopes to monitor specific frequencies and regions of the sky, collecting vast amounts of data that must then be carefully analysed to distinguish potential artificial signals from the natural radio emissions that fill the cosmos. This process presents challenges that would be difficult to appreciate without understanding the complexity of the radio universe that surrounds us. Space is not quiet at radio frequencies. Stars, galaxies, quasars, pulsars, and countless other astrophysical objects emit radio waves through various natural processes, creating a background of cosmic static that fills every frequency band across the radio spectrum. Against this backdrop of natural radio emissions, SETI researchers must search for signals that bear the unmistakable signatures of artificial origin. They look for transmissions that exhibit characteristics unlikely to occur in nature, narrow frequency bands that suggest deliberate tuning, regular patterns that might indicate intentional structure, or modulation schemes that could encode information. The challenge resembles trying to identify a single human conversation taking place in a stadium filled with 100,000 people, all talking simultaneously, except that the stadium spans the entire galaxy and most of the background noise comes from exotic astrophysical phenomena. We're still learning to understand. Earth itself contributes significantly to the difficulty of this search by generating enormous amounts of artificial radio interference that can mimic or mask the very signals SETI researchers hope to detect. Every radio station, television transmitter, cellular phone tower, microwave oven, and electronic device on our planet produces electromagnetic emissions that can interfere with sensitive radio astronomy observations. Military radar systems, aircraft navigation beacons, and satellite communication networks add additional layers of interference that must be carefully filtered out of the data. Modern civilization has essentially surrounded our planet with a bubble of artificial radio noise that makes the detection of weak extraterrestrial signals exponentially more challenging than it would be from a naturally quiet world. Despite these formidable technical challenges, SETI research continues with a patient persistence that reflects a profound kind of optimism about the nature of intelligence and communication in the universe. The researchers involved in this work understand that they may spend entire careers listening without detecting a single confirmed signal from another civilization. They accept that the odds of success in any given observation are vanishingly small, and that positive results, if they come at all, might not arrive for decades or centuries. Yet they continue their vigil, night after night, pointing their instruments toward different regions of the sky and different frequency bands, accumulating data that gradually expands our knowledge of the radio cosmos, even when it fails to reveal evidence of alien intelligence. This persistence embodies a particular kind of hope that transcends immediate expectations of success. SETI researchers are not driven by the belief that discovery is imminent or even likely within their lifetimes. Instead, They are motivated by the recognition that some questions are so fundamental to our understanding of our place in the universe that they deserve investigation regardless of the odds of quick success. The search for evidence of other intelligence represents an investment in possibilities that extend far beyond any individual career or generation, a commitment to asking questions whose answers might reshape our entire conception of life, intelligence, and cosmic community. The act of listening itself becomes a form of cosmic citizenship, a way of participating in the possibility of a larger community of minds even in the absence of confirmed contact. Every hour spent monitoring the radio spectrum, every algorithm developed to distinguish artificial from natural signals, every upgrade to telescope sensitivity contributes to humanity's readiness to recognize intelligence should it choose to reveal itself. SETI transforms our planet into a listening post at the edge of the galaxy, patient and alert for any whisper of consciousness carried on the cosmic wind. In recent years, astronomers and astrobiologists have begun to explore a subtle but potentially revolutionary shift in how we might detect evidence of intelligence elsewhere in the universe. Rather than waiting for deliberate messages broadcast by alien civilizations, scientists are increasingly focused on searching for what they call technosignatures, the unintentional traces that advanced technological societies might leave in their local cosmic environment. NASA has formally recognized technosignatures as a legitimate and promising avenue of research, defining them as evidence of past or present technology and classifying them as a subset of the broader category of biosignatures, which encompass any detectable signs of life, whether intelligent or not. This approach represents a fundamentally different philosophy from traditional SETI research, which has focused primarily on detecting intentional communication signals. Technosignatures assume that civilizations, like individual organisms, inevitably alter their environments in ways that might be detectable from great distances, even when they're not actively trying to communicate with other worlds. Just as paleontologists can reconstruct ancient life forms from fossilized footprints and feeding traces rather than complete skeletons, astronomers hope to identify alien civilizations by detecting the indirect evidence of their technological activities rather than their deliberate attempts at contact. The search for technosignatures acknowledges a profound truth about technological development. Advanced civilizations must inevitably consume energy, process materials, and modify their environments in ways that produce detectable byproducts. Every technological society faces fundamental challenges related to energy production, waste disposal, transportation, and communication, and the solutions they develop to address these challenges might create signatures visible to distant observers equipped with sufficiently sensitive instruments. One of the most promising categories of technosignatures involves atmospheric chemistry that could only result from industrial activity. On Earth, our atmosphere contains trace gases that would be almost impossible to produce through natural processes alone. The presence of chlorofluorocarbons, nitrogen oxides from combustion, and elevated levels of carbon dioxide all represent chemical signatures of technological civilization that would be detectable to alien astronomers studying our planet from dozens of light years away. Similarly, if other civilizations have developed industrial processes similar to our own, they might have altered the atmospheric composition of their worlds in ways that would stand out against the natural background chemistry we would expect from a purely biological planet. Advanced civilizations might also produce technosignatures through their energy consumption patterns. Any technological society that has grown beyond the earlier stages of development must harness increasingly large amounts of energy to power their cities, transportation systems, and industrial processes. This energy consumption inevitably generates waste heat that radiates into space as infrared radiation. Astronomers are beginning to develop techniques for detecting unusual infrared emissions, from planetary systems that might indicate the presence of large-scale technological infrastructure. Some researchers speculate about even more ambitious technosignatures that might result from civilizations far more advanced than our own. A society that has exhausted the energy resources of its home planet might construct massive engineering projects designed to capture a larger fraction of their star's total energy output. These hypothetical megastructures, sometimes called Dyson spheres or Dyson swarms after the physicist Freeman Dyson, who first proposed them, would partially block starlight while re-emitting that energy as infrared radiation, creating distinctive patterns that would be visible to telescopes capable of monitoring stellar brightness and temperature over long periods. The search for structured light patterns represents another promising avenue for technosignature detection. Civilizations that have developed powerful laser technology might use focused beams of coherent light for energy transmission, interplanetary communication, or propulsion systems. These artificial light sources would produce spectral signatures quite different from the thermal radiation emitted by stars and planets, potentially making them detectable even across interstellar distances if they happen to be pointed in our direction or if they scatter off intervening dust and gas. Perhaps most intriguingly, some technosignatures might result from a civilization's efforts to modify their local cosmic environment for purposes we can barely imagine. Advanced societies might alter the orbits of planets or asteroids to optimize resource extraction or planetary engineering projects. They might construct artificial structures in space that produce gravitational effects detectable by our most sensitive instruments. They might even engage in stellar engineering, manipulating the nuclear processes within their host stars to extend stellar lifetimes or optimize energy output for their technological needs. The beauty of the technosignature approach lies in its independence from the intentions and communication strategies of alien civilizations. Unlike traditional SETI research, which depends on other species choosing to broadcast signals in our direction using technologies compatible with our detection methods, technosignature searches could potentially identify civilizations that have no interest in communicating with other worlds, or that use communication technologies completely unlike our own. A civilization could be actively trying to hide its presence from potential observers and still leave technosignatures detectable by sufficiently advanced instruments. This shift towards seeking traces rather than greetings also reflects a more mature understanding of the challenges involved in interstellar communication and the diversity of paths that technological development might take on different worlds. Rather than assuming that alien intelligence will necessarily develop along trajectories similar to our own or share our interest in making contact with other species, technosignature research acknowledges that intelligence might take forms we haven't yet imagined while still leaving detectable footprints in the physical universe. The search for technosignatures represents a patient, methodical approach to the question of cosmic loneliness that doesn't depend on other civilizations actively reaching out to us. Instead, it transforms every exoplanet observation, every stellar survey, and every atmospheric analysis into a potential opportunity for discovering evidence of technological intelligence, expanding the search for cosmic companions from a few dedicated radio telescopes to the entire arsenal of modern astronomy. Among the many possible explanations for the profound silence that surrounds us in the cosmos, one of the most thought-provoking suggests that the vast distances between stars serve a function that extends far beyond simple geometry. This concept, known as the quarantine hypothesis, proposes that interstellar space acts as a kind of cosmic public health measure, a natural buffer zone that prevents the rapid spread of anything from one star system to another, including life, culture, technology, and potentially destructive phenomena that might otherwise sweep across the galaxy like wildfire through a dry forest. The quarantine hypothesis begins with a simple observation about the nature of biological and cultural systems here on Earth. Throughout human history, isolation has served as both a blessing and a curse for different populations and civilizations. Island communities develop unique species, languages, and cultural practices precisely because geographic barriers limit the exchange of genes, ideas, and technologies with the outside world. This isolation allows for independent evolution and innovation, creating diversity that enriches the broader tapestry of life and culture. Yet the same barriers that preserve uniqueness can also prevent mutual aid during crises, leaving isolated populations vulnerable to disasters that might be survivable with outside assistance. When we scale this principle up to cosmic dimensions, the implications become both fascinating and sobering. The light years that separate star systems from one another create isolation barriers that are far more formidable than any ocean or mountain range that has ever divided populations on Earth. While a message can cross Earth's largest ocean in a matter of hours via electronic communication, or be traversed by aircraft in less than a day, the nearest star system lies more than 4 years away, even for signals travelling at the speed of light. Physical travel requires timeframes measured in tens of thousands of years using our current technology, creating separation so complete that stellar civilizations might as well exist in separate universes as far as meaningful interaction is concerned. From one perspective, this cosmic quarantine offers profound protection for developing civilizations. If intelligence tends to arise on many worlds throughout the galaxy, then each world is shielded from potentially harmful interference during its crucial developmental phases. A young civilization learning to harness nuclear energy, develop sustainable agriculture, or establish stable political systems can do so without fear of invasion, colonization, or cultural contamination by more advanced neighbors. The vast distances ensure that each world has the space and time necessary to find its own solutions to the fundamental challenges of technological development, creating a galaxy of diverse approaches to civilization rather than a homogeneous empire dominated by whichever species first achieved interstellar travel. This protective aspect of cosmic isolation becomes particularly important when we consider how devastating contact with more advanced civilizations has often been for less technologically developed societies here on Earth. Throughout human history, encounters between cultures with significant technological disparities have frequently resulted in the displacement, absorption, or destruction of the less advanced group. European contact with indigenous populations in the Americas, Australia, and the Pacific Islands provides sobering examples of how technological advantages can translate into cultural dominance that erases centuries or millennia of independent development. On a cosmic scale, the quarantine effect of interstellar distances prevents any single species from rapidly dominating the entire galaxy, no matter how advanced their technology might become. Even a civilization capable of travel at significant fractions of light speed would require millions of years to spread across the full diameter of the Milky Way, and the energy costs involved in such expansion would be so enormous that it might be economically unfeasible even for highly advanced societies. This natural limitation ensures that the galaxy remains a diverse ecosystem of independent worlds rather than a single expanding empire. However, the same distances that provide protection against unwanted interference also prevent beneficial exchanges that might help civilizations overcome existential challenges. If a young technological civilization faces a crisis that threatens its survival, such as climate change, resource depletion, or weapons of mass destruction, the quarantine effect of interstellar space means that help cannot arrive from more experienced neighbors who might have already solved similar problems. Each world must navigate these dangerous transitions alone, without the benefit of advice, assistance, or rescue from others who have successfully passed through similar phases of development. This isolation also prevents the kind of intellectual and cultural exchange that has driven much of human progress throughout history. The flowering of science, art, and philosophy often occurs when different cultures meet and share their accumulated knowledge and perspectives. The quarantine hypothesis suggests that cosmic civilizations must forego these benefits of cultural exchange, developing their understanding of the universe in intellectual isolation that might slow their progress or lead them down conceptual dead ends that contact with alien perspectives could help them avoid. Perhaps most poignantly, cosmic quarantine prevents the formation of the kind of mutual companionship that might provide comfort against the existential loneliness that thinking beings experience when contemplating their place in a vast and seemingly empty universe. Even if thousands of civilizations exist within our own galaxy, each one remains fundamentally alone with its questions, fears, and hopes, unable to share the profound experience of consciousness with minds that evolved under different stars. The quarantine hypothesis reframes our cosmic loneliness not as an unfortunate accident of physics, but as a necessary feature of a universe designed to preserve diversity and prevent any single form of life or intelligence from overwhelming all others. In this view, the silence we detect when we listen for signals from other worlds is not evidence of emptiness, but rather the sound of a galaxy where thousands of civilizations are quietly developing in their own protected corners of space, each following its own unique path toward understanding and perhaps wisdom. This perspective offers a bittersweet comfort. We may be alone in our immediate cosmic neighborhood, but we might also be part of a vast community of solitary worlds, each one treasured and protected by the gentle quarantine of interstellar space, each one contributing its own irreplaceable voice to a cosmic symphony we may never hear but can imagine and hope for. When you consider the profound isolation that separates Earth from its nearest stellar neighbors, it's natural to wonder what technological advances might be necessary to bridge these cosmic gulfs and establish meaningful contact with other worlds. The engineering challenges involved in interstellar travel and communication represent some of the most daunting problems ever contemplated by human ingenuity, requiring us to push against fundamental physical limits while working within constraints imposed by the basic laws of energy, momentum, and time. Understanding these challenges helps illuminate why the universe feels so quiet around us, and why even our most ambitious current proposals for reaching other stars remain breathtakingly limited compared to the kind of robust interstellar infrastructure that science fiction has taught us to imagine. Our current reality provides a sobering baseline for any discussion of interstellar travel. The Voyager spacecraft, our fastest and most distant emissaries, crawl through space at roughly 17 kilometers per second, a pace that sounds impressive until you calculate that reaching Proxima Centauri would require more than 70,000 years of travel time. Even our most powerful rockets, capable of accelerating payloads to escape velocity and beyond, achieve speeds that remain negligible compared to the distances involved in interstellar space. The Space Shuttle, during its operational lifetime, reached orbital velocities of about 8 kilometers per second. The New Horizons probe, which conducted a high-speed flyby of Pluto, travels at approximately 16 kilometers per second relative to the Sun. These represent the pinnacle of current propulsion technology, yet they fall short by factors of thousands when measured against the speeds that would be necessary for practical interstellar missions. Against this backdrop of current limitations, a small number of visionary projects have begun to explore radically different approaches to interstellar exploration. The most prominent of these is Breakthrough Starshot, an ambitious research program that proposes using powerful Earth-based lasers to propel ultra-lightweight spacecraft toward nearby star systems at unprecedented speeds. The concept relies on photonic propulsion, harnessing the momentum carried by light itself to accelerate tiny probes equipped with gossamer-thin sails designed to capture and redirect laser energy into forward motion. The engineering elegance of this approach becomes apparent when you consider how it sidesteps many of the fundamental problems that plague conventional rocket propulsion. Rather than carrying fuel that must itself be accelerated along with the spacecraft, photonic propulsion draws its energy from stationary laser installations that remain safely on Earth throughout the entire mission. The spacecraft itself can be reduced to an absolute minimum, consisting essentially of a lightweight sail attached to a miniaturized electronics package containing cameras, sensors, and communication equipment weighing no more than a few grams. Breakthrough Starshot's most optimistic projections suggest that such a system might be capable of accelerating these nanoscale probes to velocities approaching 20% of the speed of light, fast enough to reach Alpha Centauri in approximately 20 years, rather than the tens of thousands of years required by conventional spacecraft. This represents a theoretical improvement in travel time by factors of thousands, transforming interstellar exploration from a project spanning geological timescales into something that might be completed within a single human generation. Yet even these remarkable projections, if fully realized, would represent only the most preliminary step toward meaningful interstellar contact. The probes envisioned by Breakthrough Starshot would conduct high-speed flybys of their target systems, racing past any planets or other objects of interest at velocities so extreme that detailed observation would be limited to brief moments during closest approach. The spacecraft would be far too small to carry the kind of sophisticated scientific instruments that have made missions like Cassini or New Horizons so scientifically productive, and their high-speed trajectories would preclude any possibility of orbital insertion or extended study of interesting phenomena. More fundamentally, the gulf between sending gram-scale scouts and establishing the kind of robust interstellar infrastructure necessary for meaningful contact remains almost incomprehensibly vast. Even if Breakthrough Starshot succeeds in demonstrating that tiny probes can be accelerated to significant fractions of light speed, scaling up to spacecraft capable of carrying human passengers, substantial scientific equipment, or even moderately sophisticated robotic explorers would require overcoming engineering challenges that belong to an entirely different universe of difficulty. The energy requirements alone present staggering obstacles. Accelerating a single gram to 20% of light speed requires approximately 900 billion joules of energy, equivalent to the total electrical output of a large power plant operating for several hours. Scaling up to a spacecraft massive enough to carry meaningful scientific instruments or human passengers would demand energy resources comparable to the total power consumption of entire nations, sustained over periods of years or decades to achieve the gradual acceleration necessary for such ambitious missions. The communication challenges compound these difficulties further. Even if we succeeded in sending sophisticated robotic explorers to nearby star systems, maintaining contact with them across interstellar distances would require communication systems far more powerful and sensitive than anything currently available. Radio signals transmitted from Alpha Centauri would arrive at Earth attenuated by factors of billions, requiring receiver systems of extraordinary sensitivity to detect meaningful data transmitted by spacecraft operating with severely limited power budgets. These engineering realities reveal why the cosmos feels so profoundly isolated, despite the theoretical possibility of interstellar exploration and communication. While physics doesn't absolutely forbid travel between the stars, it imposes energy and time requirements so extreme that even our most optimistic projections for technological development suggest that meaningful interstellar contact will remain extraordinarily difficult for centuries or millennia to come. The universe has structured itself in such a way that while intelligence can arise on countless worlds throughout the galaxy, The practical barriers to establishing contact between these islands of consciousness remain formidable enough to preserve the essential isolation that characterizes our cosmic condition. Even in our most optimistic scenarios for interstellar exploration and contact, where advanced propulsion systems successfully deliver sophisticated probes to nearby star systems, and those missions discover clear evidence of alien intelligence, the fundamental structure of space and time conspires to transform what we might hope would be a conversation into something far more like an exchange of historical documents between civilizations separated by geological epochs. The communication delays inherent in interstellar distances create a temporal trap that redefines the very nature of contact between worlds, turning every attempted dialogue into a multi-generational project that unfolds across timescales longer than most human institutions have existed. Consider the most favorable possible outcome for a mission like Breakthrough Starshot. Imagine that one of those tiny laser-propelled probes successfully reaches the Alpha Centauri system in 20 years, as optimistically projected, and discovers not just planets but clear signs of technological civilization. Perhaps the probe's miniaturized cameras capture images of artificial structures, geometric patterns too regular to be natural, or atmospheric compositions that could only result from industrial activity. The probe dutifully transmits this extraordinary data back toward Earth, sending the most important message in human history across the 4¼ light years that separate our solar systems. Even travelling at the speed of light, the fastest that information can move through the universe, according to the laws of physics, this momentous news would not reach Earth for another 4 years and 3 months. The scientists who launched the original mission, if they were young researchers at the time of launch, would now be approaching retirement age as the first signals confirming the existence of alien intelligence finally arrive at our radio telescopes. The world that receives this information would be measurably different from the world that sent the probe, shaped by more than 2 decades of technological, political, and social evolution that occurred while humanity's most important ambassadors crawled across the cosmic dark. But this 24-year delay between launch and confirmation represents only the beginning of the communication challenge. If the discovery of alien intelligence prompts us to send a more sophisticated follow-up message, perhaps a detailed radio transmission explaining who we are, where we come from, and expressing our desire for peaceful contact, that signal would require another 4 years and 3 months to reach Alpha Centauri. If the alien civilization chooses to respond, their reply would take an additional 4 years and 3 months to return to Earth. A simple exchange of greetings, the kind of basic introduction that might take 5 minutes between humans meeting for the first time, stretches across nearly 9 years when conducted between star systems. This arithmetic of delay transforms interstellar communication into something qualitatively different from any form of dialogue we experience in our daily lives. Human conversation depends on the rapid back and forth of question and response, the subtle interplay of statement and reaction that allows minds to build understanding together in real time. When you speak with another person, whether face-to-face or through electronic media, the delays involved are measured in fractions of seconds, short enough that your brain treats the exchange as essentially instantaneous. Even international phone calls or video conferences, which might involve delays of a few hundred milliseconds as signals travel through undersea cables or bounce off satellites, maintain the essential rhythm of natural conversation. Interstellar communication operates on timescales that completely demolish this conversational structure. When the delay between question and answer spans years or decades, the concept of dialogue loses all meaning in any conventional sense. Instead of engaging in conversation, civilizations separated by interstellar distances would be exchanging what amount to carefully composed letters, each one crafted with the knowledge that any response will arrive years later, addressed to a society that may have changed significantly during the intervening period. They Implications become even more sobering when you consider communication with civilizations located at greater distances than our immediate stellar neighbors. A radio signal sent to a star system 100 light years away, still within our local galactic neighborhood, would not arrive until the year 2125. If anyone there received it and chose to respond immediately, their answer would not reach Earth until the year 2225, more than 2 centuries in the future. The scientist who sent the original message would have been dead for generations. The civilization that eventually receives the reply might be as different from present-day humanity as we are from the people who lived during the American Revolutionary War. This temporal isolation reframes the entire enterprise of searching for extraterrestrial intelligence. Rather than seeking partners for conversation, we are essentially conducting a form of archaeology using electromagnetic radiation instead of shovels and brushes. When we point our radio telescopes toward distant stars and listen for artificial signals, we are not eavesdropping on contemporary alien civilizations. We are searching for messages that left their sources years, decades, or centuries ago, transmitted by beings who may no longer exist by the time their signals reach us. Similarly, any signals we choose to broadcast into space will not represent our current state of development to whoever eventually receives them. They will be historical artifacts, frozen snapshots of human civilization at the moment of transmission, carrying information about who we were and what we knew at a specific point in our technological development. By the time those signals reach their destinations and prompt any response, we may have evolved into something unrecognizable to the humans who first composed those messages. This temporal disconnect suggests that successful contact between interstellar civilizations, should it ever occur, will be less like establishing diplomatic relations and more like discovering an ancient library filled with texts written by long-dead authors. Each message will be a time capsule, a carefully preserved record of thoughts and intentions that originated in what amounts to the distant past of both the sender and the receiver, creating a form of communication that operates outside the normal flow of cause and effect that governs terrestrial dialogue. When we contemplate the profound quiet that surrounds our small planet, listening night after night for signals that never arrive from intelligences that may or may not exist among the distant stars, it becomes difficult to avoid the unsettling possibility that this great silence tells us as much about the nature of human perception and expectation as it does about the actual distribution of life and consciousness throughout the cosmos. The absence of confirmed contact with other civilizations has sparked countless interpretations, theories, and stories, each one revealing something profound about how we understand ourselves, our place in the universe, and our deepest hopes and fears about what it might mean to be truly alone in an apparently endless cosmic ocean. Human beings are natural storytellers, creatures who instinctively transform mysterious phenomena into narratives that help us make sense of our experience and our place within larger patterns of meaning. The silence we detect when we point our most sensitive instruments toward the sky has provoked an entire mythology of possible explanations, each one reflecting different aspects of our collective psyche and our assumptions about the nature of intelligence, technology, and cosmic community. Some interpretations paint pictures of galactic utopias, advanced civilizations so sophisticated that they have transcended the need for crude electromagnetic communication, existing in states of harmony and wisdom that render them invisible to our primitive detection methods. Other stories lean toward darker possibilities, suggesting that the silence results from cosmic catastrophes that systematically eliminate technological civilizations before they can establish lasting contact with their neighbors. These narratives often reflect our own anxieties about nuclear warfare, environmental collapse, artificial intelligence, or other existential risks that seem to accompany technological development. Still other interpretations invoke deliberate concealment, proposing that advanced aliens have chosen to hide their presence from younger species like ourselves, either out of benevolent caution or more ominous intentions that we can only guess at from our position of cosmic ignorance. While these psychological interpretations reveal fascinating aspects of human nature and our relationship with uncertainty, it's important to recognize that the physics we've already explored can account for much of the observed silence without requiring any of these more speculative explanations. The vast distances between stars, the enormous energy costs of interstellar travel and communication, the temporal isolation that separates civilizations across different eras of galactic history, and the fundamental challenges of detecting artificial signals against the background noise of a radio-loud universe all combine to create conditions where profound silence would be expected, even in a galaxy teeming with intelligence. The absence of obvious alien signals might not indicate an empty universe so much as an observational limitation imposed by our current technology, our brief existence as a technological species, and our necessarily parochial assumptions about how other forms of intelligence might choose to communicate. We have been seriously searching for extraterrestrial signals for only about 60 years, a time span that represents less than 1% of recorded human history and an infinitesimally small fraction of the age of the galaxy. Our search methods have focused primarily on radio wavelengths, using detection techniques optimized for the kinds of signals we ourselves broadcast, but alien civilizations might communicate using quantum entanglement, neutrino beams, gravitational waves, or exotic phenomena we haven't yet discovered or learned to manipulate. Even more fundamentally, our concept of what constitutes a detectable civilization may be profoundly limited by our anthropocentric perspective. We search for radio signals because we use radio technology, but intelligence that evolved under different conditions might develop along trajectories that bear little resemblance to our own technological path. Silicon-based minds might operate on timescales vastly different from carbon-based consciousness, sending signals so slow or so fast that we wouldn't recognize them as artificial. Collective intelligences might emerge from planetary ecosystems in ways that produce no individual artifacts detectable by our instruments. Machine intelligences might optimize themselves for efficiency in ways that minimize their electromagnetic signatures rather than maximize them. The great silence we observe, rather than providing definitive evidence about the cosmic abundance or scarcity of intelligence, serves as a mirror that reflects the limitations of our current perspective and the assumptions embedded in our search strategies. It reveals how much we still don't know about the fundamental nature of intelligence, consciousness, and technological development. It highlights the profound challenge of recognizing forms of intelligence that might be radically different from our own, operating according to principles and priorities we can barely imagine. Yet if we take seriously the possibility that the silence represents a genuine scarcity of detectable intelligence rather than merely an observational limitation, the implications become both humbling and profound. If Earth truly represents something rare in the cosmic landscape, if consciousness and technological intelligence are far less common than optimistic projections suggest, then our small planet carries a responsibility that extends far beyond the welfare of our own species. We become not just another technological civilization among many, but potentially one of the few flickering candles of awareness in a universe that might otherwise be dark and unconscious. This perspective transforms every decision we make about the long-term survival and development of human civilization into a question of cosmic significance. If intelligence is common throughout the galaxy, then the loss of human consciousness would be tragic, but not unique, balanced by countless other forms of awareness arising elsewhere among the stars. But if intelligence is rare, if Earth represents something precious and irreplaceable in the cosmic order, then our survival and flourishing becomes a responsibility not just to ourselves and our descendants, but to the universe itself, which might depend on minds like ours to observe, understand, and appreciate the remarkable cosmos that gave us birth. The silence we detect when we listen across the cosmic dark may ultimately tell us less about the presence or absence of alien intelligence than about the profound responsibility that comes with being conscious in a universe that might be far lonelier and far more dependent on the continuation of whatever intelligence does arise than we have ever dared to imagine. If the profound silence we detect when we listen across the cosmic dark truly reflects the genuine scarcity of intelligence throughout our galactic neighborhood, then the implications extend far beyond abstract questions about the nature and distribution of consciousness in the universe. This possibility fundamentally transforms how we understand Earth's role in the cosmic order and reframes our relationship with our own planet from one of casual habitation to one of profound stewardship. Rather than viewing ourselves as temporary residents of one world among countless others, we begin to see ourselves as the custodians of something extraordinarily rare and precious, a single island of awareness floating in an ocean of cosmic silence that may stretch across thousands of light years in every direction. This perspective dissolves the traditional boundaries between local and cosmic responsibility, revealing how every decision we make about the management of Earth's resources, the preservation of its biodiversity, and the continuity of human civilization reverberates with significance that extends far beyond our immediate planetary concerns. If we are indeed alone, or if intelligence is sufficiently rare that the nearest thinking beings exist hundreds or thousands of light years away, then Earth represents not just our home, but potentially the only repository of consciousness, knowledge, and cultural achievement within an enormous sphere of space centered on our solar system. In this context, our biosphere ceases to be merely the scenic backdrop against which human civilization unfolds and becomes instead the complete life support system for what may be the galaxy's most precious cargo, minds capable of contemplating the universe and understanding their place within it. Every forest that purifies our atmosphere, every ocean that regulates our climate, every species that contributes to the intricate web of relationships that maintains the stability of Earth's living systems becomes part of a cosmic trust that we hold not just for ourselves and our descendants, but potentially for consciousness itself within our region of the galaxy. The metaphor of Earth as a spaceship, popularized by environmentalists and systems theorists, takes on profound new meaning when viewed from this cosmic perspective. If we are truly isolated by interstellar distances that prevent meaningful contact with other civilizations, then our planet functions as a complete world ship carrying its cargo of life and intelligence through the cosmic dark with no possibility of rescue, resupply, or assistance from external sources. Unlike the passengers on a conventional ship, who might expect help from other vessels if their journey encounters difficulties, we must assume that Earth's biological and technological systems represent our complete resource base for the indefinite future. This recognition transforms every environmental challenge from a local problem into a question of cosmic significance. Climate change becomes not just a threat to human welfare and natural ecosystems, but potentially a threat to the continuity of consciousness within thousands of cubic light-years of space. The extinction of species represents not just a tragic loss of biological diversity, but the elimination of evolutionary information and ecological relationships that took billions of years to develop and might never arise again anywhere in the known universe. The degradation of Earth's life support systems threatens not just the comfort and prosperity of current generations, but the survival of what may be intelligence's only outpost in our corner of the galaxy. Yet this cosmic responsibility extends beyond environmental stewardship to encompass the preservation and development of the knowledge, culture, and institutions that represent humanity's accumulated understanding of the universe and our place within it. If we are indeed rare, then the libraries, universities, and cultural institutions that preserve human learning become repositories of cosmic significance, containing insights and discoveries that might represent the only attempts within hundreds of light years to understand the fundamental nature of reality through scientific investigation and philosophical inquiry. The languages we speak, the stories we tell, the artistic traditions we maintain, and the scientific knowledge we accumulate all become part of a precious cargo that must be preserved and transmitted across generations with the same care that ancient civilizations devoted to their most sacred texts and traditions. Every university that closes, every language that disappears, every scientific discipline that lacks sufficient practitioners to maintain its continuity represents a potential loss that echoes across cosmic scales, eliminating forever forms of understanding that arose through the unique historical circumstances of Earth's particular evolutionary and cultural trajectory. This cosmic perspective also suggests that our primary obligation as a potentially isolated civilization lies not in ambitious schemes for expansion and conquest, but in the more fundamental challenge of endurance and continuity. Rather than dreaming primarily of spreading human influence across the galaxy, we might focus first on ensuring that consciousness and intelligence persist on Earth for timescales that match the cosmic patience required for meaningful contact with other worlds. If the nearest civilizations exist hundreds of light years away, then achieving contact might require maintaining technological capability and cultural continuity for thousands of years, a time span that dwarfs the entire history of written human civilization. This long-term perspective encourages forms of thinking and planning that extend far beyond the immediate concerns that typically dominate political and economic decision-making. It suggests that our highest priority should be developing sustainable relationships with Earth's natural systems, creating institutions capable of preserving and transmitting knowledge across centuries, and fostering cultural values that prioritize the long-term survival and flourishing of consciousness over short-term gains in power, wealth, or territorial control. The loneliness we feel when we contemplate our cosmic isolation thus transforms into something like a sacred responsibility, the duty to maintain and develop the remarkable experiment in consciousness that began on Earth billions of years ago and might not exist anywhere else within our observable galactic neighborhood. We become not just another species struggling for survival on one planet among many, but the guardians of what may be the universe's most remarkable achievement within thousands of light years of space. While the cosmic isolation we've explored throughout this journey might initially feel overwhelming or even frightening, there exists within the very vastness that separates us from potential neighbors a profound source of comfort that operates on timescales and dimensions far larger than our daily concerns. The same immense distances and enormous spans of time that create our cosmic loneliness also provide a perspective that can transform how we understand our own lives, our worries, and our place within the grand story of existence. This perspective doesn't diminish the importance of human experience, but rather places it within a context so magnificent and enduring that it reveals aspects of meaning and beauty that remain invisible when viewed from the narrow confines of our immediate temporal and spatial horizons. When you step outside on a clear night and look up at the star-filled sky, you're witnessing photons that began their journey toward Earth years, decades, or centuries ago, carrying with them information about cosmic events that occurred long before you were born and will continue to unfold long after your individual story has ended. The light from Sirius, one of the brightest stars in our night sky, left its source more than 8 years ago, while you were living a completely different phase of your life, dealing with concerns and challenges that may now seem distant or irrelevant. The light from more distant stars carries messages from even further in the past, creating a living museum of cosmic history that surrounds you every time you glance upward. This temporal perspective offers a gentle but powerful antidote to the kinds of immediate anxieties and frustrations that can dominate our daily experience. The problems that feel urgent and overwhelming today, the social conflicts that seem intractable, the personal setbacks that appear catastrophic, all shrink to more manageable proportions when viewed against the backdrop of cosmic time and space. This doesn't mean that human concerns are unimportant or that suffering should be dismissed, but rather that the universe provides a context within which even our most difficult experiences can be understood as part of larger patterns of change, growth, and eventual resolution that operate across scales far grander than individual lifetimes. The cosmos offers this perspective freely to anyone willing to contemplate its dimensions, requiring no special training or equipment beyond the capacity for quiet reflection. When you consider that the atoms in your body were forged in the nuclear furnaces of ancient stars that lived and died billions of years ago, you become connected to processes that dwarf any human institution or conflict. When you realize that the same physical laws governing the motion of planets around distant stars also govern the chemistry of your own metabolism, you discover your membership in a universe characterized by elegant mathematical relationships that transcend all the arbitrary boundaries we construct between nations, cultures, and belief systems. This cosmic membership comes with a profound revelation about the nature of meaning itself. We often assume that significance requires an audience, that achievements matter only if they're witnessed and appreciated by others. Yet the universe demonstrates daily that beauty, complexity, and remarkable phenomena unfold continuously in regions where no conscious observers exist to appreciate them. Galaxies spiral through intricate dances across millions of years in areas of space where no intelligence has yet evolved to witness their choreography. Stars forge heavy elements in their cores through processes of stunning elegance, whether or not anyone understands the nuclear physics involved. Planets develop atmospheres, weather patterns, and geological cycles that would be fascinating to study, even if no scientists existed to investigate them. This suggests that meaning and value are intrinsic properties of existence rather than qualities that require external validation. The universe can be profoundly worth understanding, appreciating, and protecting, even if it turns out that consciousness is rare enough that most of its wonders unfold in cosmic solitude. Your own capacity for curiosity, wonder, and understanding represents something remarkable in its own right, regardless of whether similar capacities exist elsewhere among the stars. The fact that matter and energy have organized themselves in such a way as to become capable of contemplating their own existence is extraordinary, whether it happened once or a billion times throughout galactic history. This realization connects to something you've likely experienced throughout your own life: the deep satisfaction that comes from learning, exploring, and understanding, independent of whether your discoveries are unique or whether others share your particular interests. The pleasure you derive from understanding how something works, from recognizing patterns in nature, from grasping connections between seemingly unrelated phenomena, doesn't depend on being the first person to make these discoveries or on having your insights validated by external authorities. Curiosity operates as its own reward, providing meaning and satisfaction that emerge from the very act of engaging with the complexity and beauty of the world around you. This intrinsic satisfaction of curiosity and understanding provides a model for how intelligence might find meaning even in cosmic isolation. If consciousness is indeed rare in the universe, then each instance of it becomes precious, not because it serves some larger cosmic purpose, but because consciousness itself represents an intrinsically valuable phenomenon, a way that the universe becomes capable of understanding and appreciating its own remarkable characteristics. The meaning emerges from the understanding itself rather than from the social or communicative functions that understanding might serve. From this perspective, the silence we detect when we listen across the cosmic dark need not feel lonely or disturbing. Instead, it might represent the sound of a universe so vast and so patient that it provides space for countless forms of consciousness to emerge, develop, and flourish in their own time and according to their own nature, each one discovering meaning through the simple but profound act of trying to understand the remarkable cosmic story of which they form a part. The pale comfort of scale reminds us that we exist within something magnificent enough to provide perspective on any difficulty and patient enough to outlast any crisis, offering solace not through false reassurance, but through the genuine recognition that we participate in patterns of existence far more grand and enduring than anything that could possibly threaten their ultimate continuation. When we contemplate the vast loneliness that cosmic distances impose upon thinking beings, searching for forms of contact that might bridge the gulfs between stars and the centuries between civilizations, we often overlook the most plausible and immediate form of interspecies communication available to us. While we may never receive radio signals from alien worlds or detect the techno-signatures of distant civilizations, we are already engaged in an ongoing dialogue with a form of intelligence that is genuinely alien to our current experience, radically different from our present understanding, and yet intimately connected to our choices and actions in ways that make every decision we make a message sent across the only kind of space-time we can meaningfully traverse, the dimension of time itself. This alien intelligence is the future, the minds, institutions, and forms of consciousness that will emerge from human civilization across the coming centuries and millennia, shaped by evolutionary pressures, technological developments, and cultural changes we can barely imagine from our current vantage point. The humans who will exist 500 years from now will be as foreign to us as we would be to someone from the 16th century, separated not by light years of space, but by centuries of cumulative change that will transform not just their technology and social structures, but potentially their fundamental ways of thinking, perceiving, and understanding reality. Yet unlike the hypothetical alien civilizations orbiting distant stars, these future minds will definitely exist, assuming human civilization survives and continues to develop. They represent our most certain form of contact with intelligence radically different from our own, and they offer us the remarkable opportunity to participate in a conversation that spans not the impossible distances between stars, but the navigable dimension of historical time. Every choice we make, every institution we build, every piece of knowledge we preserve or allow to disappear becomes part of a message we're sending to these future beings. A communication that will profoundly influence what they become and how they understand both their past and their cosmic situation. The records we leave behind, the scientific knowledge we accumulate and preserve, the cultural achievements we protect and transmit, and the environmental conditions we bequeath to coming generations all function as elements of this temporal communication system. Just as we study ancient civilizations through their artifacts, writings, and architectural remains, trying to understand their values, their knowledge, and their hopes, future intelligences will reconstruct our era through the traces we leave in the geological record, the digital archives we maintain, and the living systems we either preserve or allow to collapse. This perspective transforms our relationship with knowledge, culture, and environmental stewardship from matters of immediate practical concern into elements of the most important communication project in which we can possibly participate. The scientific discoveries we make and record today will provide future minds with crucial information about the nature of reality, potentially helping them solve problems or answer questions that we cannot even formulate from our current level of understanding. The cultural works we create and preserve will offer them insights into human consciousness as it existed during our particular historical moment, providing them with a rich understanding of how intelligence organized itself during the early centuries of technological civilization. Perhaps most significantly, the environmental and social systems we build or destroy during our lifetime will determine the physical and cultural context within which future consciousness develops, shaping not just their external circumstances, but their fundamental relationship with the natural world and their understanding of what intelligence can accomplish when it takes responsibility for the planetary systems that sustain it. The Voyager spacecraft, carrying their golden records beyond the edge of our solar system, provide a perfect metaphor for this temporal communication project, though not in the way originally intended. While these remarkable machines were designed as messages to potential alien civilizations, they function more powerfully as symbols of our ability to create artifacts that outlast their makers and carry human achievement into futures we cannot imagine. The golden records will remain readable for millions of years, long after every person involved in their creation has died, and long after human civilization has either disappeared or transformed into something unrecognizable. These spacecraft remind us that even relatively simple artifacts, when designed with sufficient care and foresight, can serve as bridges across enormous spans of time, carrying messages from one era to another with remarkable fidelity. The scientific knowledge encoded in our libraries, the genetic information preserved in seed banks and biological repositories, the artistic achievements stored in museums and archives, and the institutional wisdom embedded in our legal, educational, and cultural systems all function as golden records of a sort, designed to carry the best of human achievement forward into futures that will inevitably be shaped by how well we fulfill our role as trustees of the human enterprise. From this perspective, our cosmic loneliness transforms into a profound opportunity for temporal communication that dwarfs in significance any hypothetical contact with alien civilizations. The future minds we're shaping through our present choices will possess capabilities and perspectives that may seem as alien to us as any intelligence that might exist around distant stars. They may have solved problems that appear intractable to us, developed technologies that seem magical from our current perspective, and achieved forms of understanding that fundamentally transcend the limitations of 21st century human consciousness. Yet these future intelligences will also be our descendants, carrying forward the consequences of our decisions and building upon the foundations we provide them. They represent the nearest alien intelligence we're ever likely to encounter, strange and undiscovered, yet intimately connected to every choice we make about how to live, what to preserve, and what kind of legacy we want to leave for minds that will someday look back at our era as we now look back at ancient civilizations, trying to understand what we valued, what we understood, and what we hoped they might accomplish with the inheritance we leave behind. And so we return to where we began, standing on the shore of our small rocky planet, as it spins through the cosmic dark, carrying with it its cargo of minds and dreams and questions that reach toward distant stars. But now, after this long journey through the mathematics of loneliness and the physics of isolation, that familiar shoreline metaphor has expanded and deepened, revealing dimensions of meaning that were invisible from our initial vantage point. The dark ocean that stretches beyond our world no longer appears simply empty, a vast void waiting to be filled with human ambition and discovery. Instead, it has become something far more subtle and profound, an endless sea that may contain countless other shores, each one as real and precious as our own, each one supporting its own communities of consciousness that gaze across the same dark waters we contemplate each night. Imagine, if you will, an archipelago of cosmic proportions scattered across the galaxy, with each inhabited world functioning as its own island of awareness, surrounded by the protective moat of interstellar space. On some of these distant shores, minds very much like ours might be taking their first tentative steps toward understanding the universe, developing agriculture, and writing systems, discovering fire and mathematics, beginning to ask the same fundamental questions about their place in the cosmic order that have driven human curiosity for thousands of years. On others, intelligence might have been asking these questions for millions of years, having developed forms of understanding so advanced that their perspectives on existence would seem as foreign to us as our scientific worldview would seem to our ancestors, who first looked up at the night sky and wondered what those points of light might be. Each of these imagined worlds would possess its own sunrise and sunset, its own seasonal cycles and weather patterns, its own evolutionary history stretching back billions of years to the first simple molecules that learned to copy themselves and began the long journey toward consciousness. Each would have developed its own languages and stories, its own approaches to art and music and mathematics, its own ways of organizing society and transmitting knowledge from one generation to the next. Each would face its own unique challenges related to survival, sustainability, and the continuation of consciousness across cosmic timescales. Yet for all this potential richness and diversity, for all the remarkable possibilities that might exist on countless worlds throughout our galaxy, the fundamental structure of space and time ensures that these islands of consciousness remain essentially isolated from one another, separated by distances and communication delays that transform the cosmos into a confederation of solitary worlds rather than a connected community. This isolation is not the result of cosmic cruelty or unfortunate accident, but rather emerges naturally from the basic physics that governs motion, energy, and information transfer across interstellar distances. In this view, our cosmic loneliness takes on a different character entirely. Rather than indicating that we are alone in an empty universe, it suggests that we may be part of something far grander, a galaxy-spanning community of isolated worlds, each one developing its own unique forms of consciousness and culture, each one contributing its own irreplaceable perspective to the cosmic story, yet each one fundamentally alone with its questions and discoveries and dreams. The silence we detect when we listen across the interstellar night becomes not evidence of emptiness, but rather the natural consequence of living in a universe structured to preserve the independence and diversity of whatever intelligence might arise within it. This perspective transforms the night sky from a source of existential anxiety into something approaching cosmic comfort. When you look up at the stars from your backyard or through your bedroom window, you might now see not an empty void that highlights our isolation, but rather a vast community of potential worlds, each one potentially harboring its own forms of consciousness, each one facing similar challenges related to survival and understanding, each one contributing to a galactic symphony of intelligence that unfolds in cosmic solitude, but connects through the shared experience of being conscious in a universe vast enough to contain infinite possibilities for wonder. The mathematics of distance and time that create our isolation also create the conditions within which diversity and independence can flourish across cosmic scales. The same physical laws that prevent easy contact between worlds also ensure that consciousness, wherever it arises, has the space and time necessary to develop according to its own nature and discover its own approaches to the fundamental questions that thinking beings inevitably confront. The universe, in its apparent emptiness, provides the ultimate freedom for intelligence to explore what it means to be aware, to be curious, and to be capable of contemplating existence itself. Tonight, as you settle into sleep, you might find comfort in this expanded vision of cosmic community that operates not through direct contact, but through the shared experience of consciousness arising in a universe magnificent enough to support countless forms of awareness, patient enough to allow each one to develop in its own time, and structured in such a way that the very distances which isolate also protect and preserve the precious diversity of minds that may exist throughout the galaxy. The night sky becomes both mystery and comfort, an invitation to wonder rather than a demand for answers, a gentle reminder that you are part of something far larger and more remarkable than could ever be contained within the boundaries of any single world, no matter how rich with life and thought and dreams that world might be.